All right, so today we're talking about inverse functions. Just make sure it's going to go on page 23. Hold up on the blue just for the moment. But please make sure you do define your goal, okay? You guys are going to be able to use online tests to determine inverse functions and then also find inverse functions algebraically as well as graphically. That is what we're going to be talking about today. Now, you've heard of a different line test, right? You guys remember this from the first unit? Vertical line test. And what did the vertical line test tell you? Exactly. It told us that we had a function. So we would take a vertical line and we would move it from left to right to see if the curve would touch that vertical line more than once. Because if it did, it told us that it was a function. Okay, well, the horizontal line test does something similar, except this time it's a horizontal line. We're going to move it not left and right, but up and down. And this is actually going to tell us something a little bit different. So we're going to talk about that some as well today. Okay? Well, let's start. What is an inverse? Okay? What is an inverse? Well, an inverse function is a set of ordered pairs obtained by the exchange of each ordered pair. So in other words, you're basically switching the x and y coordinates to find the points on the inverse, okay? To find the points on the inverse. So basically we have a set of ordered pairs in which we're basically going to take the x and y coordinates of the original function and we're going to switch them. When we switch them, we end up getting the points that are located on the inverse of our function. Okay? And that's how that is an inverse thing. So we're going to look at an example together, one on your own. And it's going to kind of go back into Unit 1 a little bit. So we're going to first revisit a few things about functions as well. Okay, but we just reviewed that. So let's take a look at this example. We have a 1, 2, 4, negative 2, and 3, 2. If you guys remember when we first did functions and finding domains and ranges, we dealt with ordered pairs like this, okay? So at 1, 2, 4, negative 2, and then 3, 2. Is this a function? Are these set of ordered pairs? Is that a function? Yes, it is. This graph here just as a visual. I didn't include it into your notes, but I was just using it as a visual. Does it pass the vertical line test? Yes or no? Yeah. Yes, it does. Another way you can look at a function was there was, one input for every output, okay? No two x's repeated, right? That's what makes something a function. What's the inverse? Well, all we have to do is what? Plot the x and y. So the first order pair is going to be 2, 1, and then negative 2, 4, and then 2, 3. It's a quick switch for the points. Just double checking, make sure you didn't mess with anywhere. And now I'm going to ask you, is the inverse a function? No? How do you know? There are 2 of the same x. The rules still apply. You cannot have 2 of the same x and be a function. So they're 2 of the same x's. That's what makes it not a function. The inverse is not a function. Okay? Do that next example on your own. Give you a minute with that. So, Shay, is this a function? Yes. Good stuff. What is the inverse? What's the inverse, Nicholas?
4 negative 2.
Uh-huh.
Negative 4 3. And 5 negative 8.
Good stuff. Christian, is this the inverse? I'm sorry. Is this inverse a function? That's what I'm saying.
Yeah.
Yes, it is. And how do you know? None of the x's are the same, or none of the x's
What about 4 negative 4?
where?
About 4 negative 4.
Now, even though they're the same number, one's positive, one's negative. So both of them either would have to be positive, both of them would have to be negative in order for the inverse not to be a function. Like how in the other example, they were both positive too, making the inverse not a function. inverses, okay? You need to keep in mind that inverse basically means switch x and y, okay? Because every function and its inverses, they are symmetrical, okay? Or reflections of one another across this line, y equals x. Y equals x is a linear line. It's a linear function where the slope is 1 and it crosses through the y-axis at 0, okay? Every function and its inverse are going to be basically reflections over that line. And so if you ever have to graph the inverse of a particular function, the easiest way to do it is, because, unlike being reflecting over the y-axis or the x-axis, you pretty much can just say, okay, how far are these points away from these axes and just go to the other side. It's a little different when you have a diagonal line. But if you remember, inverses means to switch your x and y's. For me, in my personal opinion, the easiest way is to take the points that are on your original function and switch them. Okay? So this point, right here, what is going to be the point on the inverse?
4, -5.
4 and -5. This point right here is going to be what? 1, -3. All these points that I'm writing over here in red are going to be the points that are on my inverse and reflect over this purple line here. What about this point? -1, 1. And the last one? So when I plot them, I think I accidentally cut off -5 on the other paper, so I apologize. And I connect them. If I were to fold at that purple line, that hopefully you guys might have drawn on your paper as well, so you can have that visual there, you will see that like this part of the curve is right there. When you say that this part is reflection over the line for that half, and vice versa, there you go. That's what it should look like, okay? Now when you fold it, it should lay on top of each other. Is there a way to tell if an inverse is a function? Yes. That's what the horizontal line test is for. The vertical line test tells you if you have a function, it tells you if your inverse is a function. And again, the same rules still apply. It should not cross a horizontal line more than once in order for the inverse to be a function. Okay? So you guys already knew about the vertical line test that told us if we had a function. It was the horizontal line test that tells us whether or not our inverse is a function. So now you'll be able to look at a graph and say, yes, my inverse is a function. Okay? Yes?
Does it have to be special meaning, like say it's 1-to-1 function?
1-to-1. We covered this in the problem of the day. Okay? 1-to-1 basically means that it passes both tests. Not only does it pass the vertical line test, but it also passes the horizontal line test. Okay? So that picture from this slide, not the red one, but the one that was in black, the original one, is that function 1-to-1? It passes the vertical line test and it passes the horizontal line test. Okay? What about this function? Is this function 1-to-1? So is the graph a function? Is the inverse a function? No. So because it doesn't pass the horizontal line test, our inverse is not a function, and that tells us that it's not 1-to-1. Okay? Real quick, I want to add in something. You don't have to write this down, but this is more of just a review. Okay? More of just a review of a couple of things. Okay? All right. So review your parent functions. Real quick. What type of parent function is this? What type of parent function is this, Michaela? Give me the name. You don't have to actually give it like the equation. Just give me the name. Or give me the equation. Whichever one's easier. It's going to be 8. It's going to be 8. Christian. function, okay? It is a linear function. Now, does this linear function, is this inverse a function? Yes or no? Anybody?
Yes.
Yes, it passes the horizontal line test, okay? Let's go a different one, okay? What is this parent function right here, Tanner? Just that's square root of amount, Seth. The absolute value. When absolute value makes that b. Say value b. Okay? Is this inverse a function? It's no, because it's pass the horizontal line test. No, it doesn't. It hits twice. Okay? So no, the inverse here, no inverse function. I mean, there is one, but its inverse is not a function. I mean, we can still switch the points, but that makes tells us that our inverse is not a function. What's another parent function that we have? Look, we have the square root of x. We have the square root of x. That looks like this. Is the inverse a function? Yes, it is. It passes the horizontal line test. What's another parent function that we have? And what's another parent function? Alright, you got that one. Huh? Quadratic, yes. Quadratic, that's x squared. What does that look like? Looks like a U. Is this a function?
Yes.
Is it a function? Yes, it passes the vertical line test. Is this inverse a function? No, it does not pass the vertical line test. So the quadratic functions are not one-to-one. They have to pass both. Is the square root function one-to-one?
Yes.
Yes. What about the not absolute value, greatest integer function? Yes, but no. What's yes and what's no? That's the step graph.
Yes.
Yes to what? To being a function. No to the inverse, because those little horizontal lines right there are going to make it so that it doesn't pass the horizontal line test. Everybody understand that?
Yes.
Okay, let's see. So that's 1, 2, 3, 4, 5. There's 3 more. What 3 am I missing? Give me one of them that I'm missing. I'm missing cubic, reciprocal, and constant. Cubic looks like this, and I know I'm all over the place in the screen. Is this one-to-one? Yes. Now the way I graphed it was completely wrong. Okay? The real cubic function looks like this. This is one-to-one. Passing vertical and horizontal reciprocal. Is it one-to-one? This was actually yes. It never touches. It continues to decrease. And my constant, one-to-one? No. Doesn't pass the horizontal line test. It's the horizontal line, so it can't pass it. Just a good review. Just kind of beat that into your brains, okay? But inverses of functions. To find the inverse of a function algebraically, okay, there are a few steps. You replace f of x with y, and you switch x and y. Remember, inverse is all about switching. Whoa, I can't count. No, I think what I had to do was I combined 1 and 2. So it should very much say 2, and it should very much say 3. No, look, because I combined replacing and switching into 1. That was originally 1, 2, 3, 4. But I was like, gosh, some of these steps. Because some of you guys automatically replace f of x with y anyway, so it's really kind of not like a step. You already know that f of x is fine. But to find it algebraically, you switch x and y, and then you solve for y. Once you do that, you need the notation that means inverse. So this notation right here with a -1 as the exponent, that means inverse. And of course, just like with anything that we do, we need to state any restrictions on the domain. And these are the steps to find algebraically what the inverse function is. We're going to find the inverse of this. F of x equals 2x minus 4. Okay? Before we get started, what does this look like? It looks like a line. So, is the inverse a function?
Yes.
Yes. So we need to make sure that we include that notation. So the first thing we need to do is replace f of x with y. And then we need to switch. So x equals 2y minus 4. Okay? Now, do you have to do that very first step? No, you don't have to. Some of you guys automatically know f of x is y, so you just go ahead and go to the second line and you switch them, okay? That's fine. You do not have to do that very first line. But once you switch x and y, then you solve for y. How do you get y by itself? Here. And then divide by 2. And because our inverse is a function, then we can use our proper notation and replace y with f to the negative 1 of x and write our function. Do you have to do that second to last step? No, you don't have to, but you do need that very last step. Because the only other way to simplify would be 1/2 x plus 2. I mean, if you did that, that's totally fine. Totally fine. Are there any restrictions on our domain?
No, it could be 0.
Could be 0. Because where's our variable? It's on the top. So we really don't have any restrictions. And so maybe that is good to do. To actually write it as 1/2 x plus 2. Because in that way you'll be able to see it more like a linear function. And all lines don't have any restrictions on their domains. Okay? Questions? Let's do one a little harder. This is like the easy level. Okay, let's go to the medium level. Okay? F of x equals 5 over x minus 2. First thing I need to do is what, Angie? Replace x and y? Or switch x and y? Switch x and y. Wait, so what should I write?
F of y. Now y is equal to 5 over x minus 10.
Okay.
And then it's going to be x is equal to 5 over y minus 2.
Yep. Y minus 2. Okay, good. Now from here, what do I need to do? What do I need to do, Mike?
Get rid of the 2, so add it to the x. Or would you get rid of the 5 first?
Y minus 2.
Okay. Couple of things. You gotta multiply because you just can't take just the 2 because the 2 is attached to the y. So if I take the 2, I gotta take the y and the minus with it. Okay.
So multiply by 1/3.
But I can't necessarily do that either. I mean, if we did, I think we can kind of make a little bit more of a bigger problem than whatever it needs to be. The easiest, and honestly, to each his own. Depends on how you originally learn how to solve equations. But whenever you're given a fraction, if you get rid of the fraction first, it makes things a lot simpler because you're only dealing with like quote unquote whole numbers. Okay? And in this case, I have x times all of y minus 2. So I'm going to write that a little bit differently, just so that when I look back, I know that x is being multiplied by y minus 2. Now I'll take a volunteer on this one. What can I do for here? Because I need to solve for y. Okay. I can divide by x. Because the goal is to get y by itself. And when I do that, I'm left with y minus 2 equals 5 over x. And the last thing I have to do is what? Add the 2. notation, I need to double check. This original function, this f of x, what do you think it's going to look like? What parent function is this most close to? 1 over x, which was the reciprocal function. Did the reciprocal functions pass the horizontal line test? So we can use the notation of f to the negative 1 of x to write it. We only use that notation if our inverse is a function. Okay? So a lot of these problems, is the inverse a function, and if so, find the inverse. So you always want to check first to see if you do have an inverse before you go through all the work and it really not have an inverse. Make sense? Yes, we do have to state limitations. What are they? Very good. Right? Now I want you guys to give number 3 a whirl on your own. And then I'll check back in. This looks like a parabola. Does it pass the horizontal line test? No, so its inverse is not a function. But we could restrict this domain so that it did, so that we do have an inverse. Okay? Real quick, good review here. What transformations were done to the original parent function? Right 1, up 2. So this basically went to the right 1 unit and up 2 units. Okay? Now if we restrict the domain, let's say we just cut it in half, right? And we only looked at one side of this function. So just the right side. Would the right side pass the horizontal line test? Yes. So if we restrict the domain, okay? That's all the x values that are, is 1 included? Greater than or equal to 1. So if we restrict the domain, we're only looking at the right side of the parabola. And if you think about it, before we moved it to the right and we moved it up, it was originally centered right here, wasn't it? So we're really only looking at like the positives. So we can still go through the process of switching x and y and solving for y. First thing we need to do is subtract 2 and then square root. Now I know a lot of you guys forget that when you take the square root in an equation, you always need to remember a little symbol, plus or minus. But because we restrict the domain, we're only looking at the positive values. Okay? Add 1, and yes, we would have what you said. Okay? But unless we restrict that domain, we're not going to be able to say it's f to the negative 1 of x. Make sense? Okay. And just like how we said earlier as well, what restrictions do we have on the inverse? X has to be what? Questions? Basis? Any questions? All right. We're going to take a pause. Blue, your phone needs some space. We're going to do just a few more notes. Just a few. So we're going to take a few more notes. Okay? Just on verifying inverses. Okay? Because maybe you won't be asked to find the inverse. Maybe you'll be given 2 functions and you'll be asked to determine whether or not they are inverses of each other. And so the way that you do that is what you see up there. What does that notation mean when you have f and then f to the negative 1 of x on like the inside? What does that mean?
You put the inverse into the original function.
You plug the inverse into the original function, and when you do that and simplify, you should get x. And vice versa. If you plug the original function into the inverse, you should get x. Not 1, not 2x, but actually x. That's how you determine if two functions are inverses of each other. You basically just do the composite. Okay? You plug one into the other. And then do the opposite. Plug the other. And that's what we're going to do. We're going to do 2 examples of this. The first one we'll do together. And then the second one I want you guys to try on your own. But we're going to actually determine if f of x 6 over x minus 4 and 6 over x plus 4 are actually inverses of each other. Okay? So, first thing we need to do is f of g of x. So we're going to plug g into f. So here's f. I'm going to actually plug that 6 over x plus 4 in for the x, and we have minus 4. What happens here?
The 4 is
Allowed that positive 4 and that negative 4 cancel each other out, so I'm left with 6 over x. Now who remembers how to divide fractions? It's 3 letters. Keep, those are the words, but keep, change, flip. Okay? KCF. That keep stood for what? You keep the numerator. You changed the sign to what? Multiplication, and then you flip the denominator. So you basically have 6x divided by 6, which is just what? X. So far, so good. But you just can't do one of them. You got to do the other one as well, because there will be ones where f of g of x will equal x, but g of f of x won't. So now we're going to go the other way. We're going to plug f into g. So I'm going to plug 6 over x minus 4 in for x into the g function. What I have to do with that first function, that first part? Can't cancel them out the way they are, because technically this minus 4 is in a denominator that's in another denominator. How do you divide fractions? Keep, change, flip. Keep, change, flip this. It's going to turn to x minus 4 over 6. What do you think happens to those 6's? They cancel out. So you're left with x minus 4 plus 4, and what happens to the 4's? So you are just left with x. Are they inverses of each other? Yes. So all you're doing is composite. F into g, g into f, they should both equal x, and you got inverses. If they don't, no inverses. Your own. Are they inverses of each other? No. Which one did not give you x? Which way? F of g of x. So when you take g, you plug it in, it would have been the square root of x squared minus 10, all being squared plus 10. What happens when you square a square root? It cancels out, but it doesn't change anything underneath the radical. The 10's cancel out, but that is not x. It is x squared. So because it does not equal x, these are not inverses of each other. Yes?
If you were plugging in f into g, why wouldn't that whole piece of
Well, when you plug f into g, that's different. When I plug f into g, I have x squared plus 10. You square that, and then you subtract 10. So you actually have to FOIL this. You get something real crazy, nasty, and this is definitely nowhere near x. Even if you try to simplify this sum, this definitely does not equal x. you did that first one, once you saw it didn't equal x, you can stop right there and say not equals. Okay? So even though it was like the opposite, one was a plus, one was a minus, one had square root, one had square, doesn't necessarily, okay?